Okay, this is quite a useful method where you have three forces which are in equilibrium. Well, now you already know that if you have a particle which is being acted upon by three or four or more forces, then the resultant force in any direction will be zero. Now, up until now, we've looked upon that as the forces acting to the right will equal the forces acting to the left, forces acting up will equal forces acting down. But if we think of the forces as vectors, then in vector terms, what this means is that if the three forces are in equilibrium, then the sum of their vectors will be zero. So the sum of the vector forms of the three forces will be zero. Now, diagrammatically, it really helps here, because what it actually means is that if we take these three forces, I'm just going to do it, and we draw them what I would call nose to tail. So if you draw the three vectors nose to tail, so where one vector finishes, the next one starts, then those three vectors will make a closed triangle. Let me explain how that works. Okay, so I'm going to take each vector and I'm going to redraw it. So let's say, I'm going to start with that. I'm going to leave that one where it is. I'm going to now draw this one over here. So the nose of that one joins to the tail of this one. And this vector then goes here. So by changing the positions of those three vectors, what I've got is a triangle, and then depending on the question, I can use sine rule, cosine rule, just normal SOHCAHTOA trigonometry, as would be the case here, and I should be able to solve problems. So don't forget, if you've got three forces, it'll only work with three, otherwise the trigonometry gets too complicated. If you are told that they are in equilibrium, you can draw the three forces nose to tail and form a closed triangle in which you can do trigonometry. So let's have a look at an example like that. Okay, so here's an example. Let's say we have three forces, or we have a particle which is being acted upon by three forces. So here is our particle, and let's say our particle is being acted upon by a force of 9 newtons vertically downwards. Let's just write that on. So we've got 9 newtons there, and then by another force of, where are we? Another force of 7 newtons in that sort of direction. Let's just write that on. So 7 newtons, and another force acting in this sort of direction, which has a magnitude of 5 newtons. And let's say we're also told that the particle is in equilibrium, which means that the vector sum of those three forces is going to be zero. And let's say that our job is to find out, the 9 Newton forces, as I've said, is acting vertically downwards. But let's say what we actually want to find out is the angle between the 5 Newton force and the vertical, let's call that alpha, and the angle between the 7 Newton force and the vertical, let's call that beta. Okay? Okay, the first thing I'm going to do is I'm going to redraw the three vectors nose to tail. So for on here, I'm just going to clone the vector. So let's start off with my 5 Newton force. It's going to be going in that direction. And then let's take the I'll take the 9 Newton force next. So let's just clone that. And let's have that drawn so that it is nose to tail. So basically the end of the 5 Newton force becomes the beginning of the 9 Newton force. And then the 7 Newtons over here, let's just clone that, is going to form my closed triangle. Let's just pop that there. It's not perfect, but we get the idea. If it was perfectly in equilibrium, that's what it would look like. So there's my three forces. Okay, and let's just put the dimensions, let's just put the magnitudes on. So that's my 9 Newton force, that's my 7 Newton force over there, and then the 5 Newton force is going in that direction. And as we've said, we know that the vector sum is going to be zero. So basically this is a closed triangle. Right, let's put alpha and beta onto the diagram. Now alpha is the angle between the 9 Newton force and the 5 Newton force. So actually if I just extend upwards here, there's the 9 Newton direction, here's the 5 Newton direction, so that angle there is alpha. And if I draw that within the triangle, this angle here is alpha, so I should be able to find that easily enough. Beta is the angle between the 9 and the 7, so if I just extend the 9 down here and the 7 in that direction, beta, you can see, is this angle here. Now it becomes fairly straightforward trigonometry. I'm just going to rub out these bits over here because they're not particularly helpful, and neither are these. I'm just going to confuse the issue. Okay, so if I just label my triangle as I normally would for the cosine rule, I'll label it ABC in that direction. So there's little b, there's little a, there's little c. By the cosine rule, then, I can see that cos alpha is going to equal b squared plus c squared minus a squared divided by 2bc. So that's going to be, what's that, 5 squared plus 9 squared minus 7 squared divided by 2bc, or that's 2 times 5 times 9. Now that comes out as, what are 57 over 90. And from that we can find out that alpha is actually just 50.7 degrees. I'm not going to carry on, but we can then do the same for beta using the cosine rule, different sides. Anyway, it just gives us a much easier way of working out missing angles. If we were to use the other method, which I've shown you so far, if we're looking at the forces acting right will equal the forces acting left, we're going to have 7 cos 90 minus beta is going to equal 5 cos 90 minus alpha. And that's actually quite nasty. We're going to end up solving simultaneous equations in sines and cosines. A little bit nasty. This method, as long as it's 3 forces, and as long as you're told they are in equilibrium, draw them as a triangle, and the trigonometry becomes a lot simpler.